Hi guys, welcome to Night Science Stories. Imagine a sky that never cleared, a horizon that never stopped shimmering, and a world where the sound of rain was the heartbeat of the planet itself. There is a hypothesis that for somewhere between 20 and 30 million years, the young Earth knew unbroken rain. Not showers, not seasons. A planetary downpour so persistent that it carved the first oceans and tempered stone into soil. Whether this vision is exact truth or poetic oversimplification, the science behind it is rich, careful, and wonderfully calming to explore. Let us walk through it together, step by gentle step. Begin with the earliest Earth, a time geologists call the Hadean Eon. The newborn planet was still gathering itself after a collision with a wandering body roughly the size of Mars. That encounter very likely melted a vast fraction of the crust and lofted a storm of vapor and rock into orbit. Out of that ring of debris, the moon condensed, and below it, the Earth simmered like a sea of magma. In that world, air as we know it did not yet exist. The sky was a cloak of vapor and volcanic gases that exhaled from the molten surface. Every mountain that would ever be built and every valley that would ever form slept as minerals in a red, hot ocean of rock. The clock of rain had not yet started, but the seeds of it were already there, dissolved in stone as water waiting to be set free. Where did that water come from in the first place? The answer is not a single sentence. Some of it was born with the planet trapped in minerals deep in the mantle. As the interior melted and then cooled, that water escaped as vapor, a process called degassing. Some of it arrived from far away, carried by comets rich in ices and by water-bearing asteroids. Scientists weigh these possibilities by comparing the subtle fingerprint of hydrogen in ocean water with that in comets and meteorites, looking at the ratio of deuterium to ordinary hydrogen. No single source matches perfectly, which suggests a blend. The Earth was a careful bartender. It mixed mantle gases with gifts from the outer solar system and poured them together into a sky that thickened with steam. Picture that atmosphere as a cocoon. When pressure and temperature are high enough, water becomes a special fluid called supercritical. It is not quite gas and not quite liquid. In that state, it flows like a ghost through pore spaces in rock, pulls out chemical elements with ease, and condenses as soon as it touches anything even a little cooler. The young Earth wore a supercritical shawl. Whenever a patch of crust cooled, the vapor condensed. Whenever it condensed, the surface warmed again from the release of latent heat, and the cycle continued. Clouds were not patchy islands, but an almost continuous ceiling, sun filtered and weak, colors muted to a permanent dawn. Here enters the idea of long unbroken rains. If the supply of vapor from the mantle and from the last waves of infalling comets stayed high, and if the sky remained saturated because the crust could not cool quickly enough to stop condensation, then the planet would have known a steady planet-wide rain for millions upon millions of days. The phrase uninterrupted rain is a simplification because storms would still pulse and winds would still move moisture from place to place. Yet the overall effect would have felt like continuity. If someone could have stood there with a hand outstretched, that hand would rarely have been dry. The physics of such a rain is almost soothing. Imagine the energy books of the planet. Sunlight arrives. A portion is reflected to space by the cap of clouds. Another portion warms the surface and the lower air. That warmth returns upward partly as infrared radiation and partly as water vapor rising from warm rock and warm pools. When that vapor condenses to droplets, it releases heat into the cloud deck and into the troposphere, the low blanket of air where weather lives. Heat is thus moved upward by the elevator of condensation, a process we can still watch today when towering storm clouds build and turn their tops into anvils. On the ancient Earth, the elevator never rested. Every moment, somewhere above the still forming crust, vapor was condensing into rain and drizzle, and every moment the fall of those droplets returned water to the ground where it could pool, flow, and quietly sculpt. There is an old paradox to address. The sun of those days was fainter than it is now, shining perhaps at about 70% of its present power. If that were the only factor, the Earth would have been a cold marble. Yet the young planet was not frozen. The solution to that paradox is comfortingly simple. Greenhouse gases were plentiful. Carbon dioxide and water vapor are very effective at returning infrared heat back to the surface. Add to them a little methane and traces of other volcanic gases, and you have a blanket thick enough to keep the world in a warm range even under a weaker sun. The cloud cover also acted as a thermostat. Very thick clouds reflect sunlight and cool the surface, while the greenhouse effect of water vapor warms it. Together they can hold temperature steady over long spans. In such a regime, the rain does not stop because the ingredients for condensation are always present and the atmosphere keeps replacing what falls. Volcanoes were the true metronomes of this weather. Even as the crust cooled and stiffened into plates, the interior remained hot and convective. Every eruption fed the sky with more water vapor and with carbon dioxide, while sulfur-bearing gases reacted in the air to create tiny aerosols. Those aerosols served as seeds for cloud droplets. The more seeds in the sky, the more readily vapor turns into liquid. In that way, the volcanic heart of the planet did not simply build mountains. It built weather, too, pumping the atmosphere full of the matter and dust that encouraged cloud formation. From the first puddles, the transition to seas and then to an ocean was a matter of persistence. Water gathers itself wherever gravity allows. The early crust was mostly basalt, dense and dark, formed from quickly cooled lava. When water pooled on basalt, it interacted with the mineral olivine and other components to make clays and to lock away carbon in rocks. Those chemical reactions gently lowered the saltiness of early runoff and removed a fraction of the carbon dioxide from the air, which allowed the atmosphere to thin and cool further. As the crust fractured and sagged along great faults, large basins formed. Think not of sudden cataclysms, but of a slow settling of a quilt on a bed, with dips that became catchment bowls. With time and continued rain, those bowls linked into a globe-girdling ocean. We do not have photographs from that era, but we do have crystals that act like extremely old notes. Among the most famous are tiny zircons found in the hills of Western Australia at a place named Jack Hills. Some of these crystals are more than 4 billion years old. Their oxygen isotopes suggest that they formed in the presence of liquid water, not just vapor, which means a hydrological cycle existed very early. There are also ancient sedimentary rocks whose textures hint at water-laid deposition. Each line of evidence is sparse and subtle, yet together they trace the outline of a world that was already wet long before life left its first obvious fossils. The chemistry of such rains would not have been the same everywhere or at every moment. Early volcanic gases included sulfur dioxide and nitrogen oxides that react with water to make acids. That means many showers were acid rains with a bite strong enough to dissolve minerals quickly. In doing so, those rains taught the ocean its first flavors. Sodium, chloride, magnesium, calcium, potassium, and sulfate leached from fresh rocks and flowed along the newborn riverbeds. When these ions met in solution, they created the saline signature of the sea. The ocean became a giant chemical laboratory where the balance between inflow from rivers and precipitation of minerals set the long-term salt content. Even today, every grain of beach sand that was once a feldspar crystal records a little of that ancient dissolving. It is not a violent story. It is a story of relentless patience, drop by drop. Consider the sound of such a planet. There would be wind, of course, and waves, but above all, there would be the constant soft percussion of water on many surfaces. Ash cones built from eruptive fragments would hiss and collapse as rain infiltrated them. Lava fields would crackle as they cooled under sudden showers. The first lake shores would gurgle. Steam would lift in veils from warm ground. In low places, the air would carry the smell of dissolved metals and sulfur. Light would be the kind that painters call diffuse, as though the world had chosen the palette of an overcast morning for the background of its first chapter. If the rain paused anywhere, it would have been at high altitude where temperatures were coldest and precipitation froze into early snows and hail. Yet even there, melt would return water to the general flow. That melt would slip through pores in volcanic ash and through fractures in lava to become the earliest groundwater. The newborn planet was learning to store water not only on its surface, but inside its crust. In quiet aquifers, the rains found a memory. In later ages, those aquifers would serve life as wells and springs. At the beginning, they were simply the places where the planet kept part of its gift to itself. All the while, the balance between cloud and ocean evolved. A thick ceiling of clouds keeps a surface from either boiling or freezing quickly, which makes continuous rain more plausible over long intervals. Yet, cloud physics is a dance of scales. Microscopic droplets collide and join until they are heavy enough to fall. Turbulent eddies carry some upward again to grow larger. The presence of tiny dust grains and sea salt particles encourages droplets to form, and the chemical makeup of those particles affects the size of the drops and their ability to reflect sunlight. In the Hadean atmosphere, there would have been no shortage of such seeds. The sky was a workshop manufacturing its own tools. As seas spread and deepened, they altered the climate machine in return. Liquid water is the champion of heat transport. It carries warmth by currents. It evaporates to move heat upward, and it releases that stored heat when it rains. The first ocean would have smoothed extremes between the equator and the poles. It would have helped erase the daily difference between day and night. It would have lent the planet the ability to keep the rain falling, not as a frantic flood, but as an almost contemplative continuity. The moon, our companion born of that early collision, played a part too. Its new orbit stood closer than it does now, and so its tides were stronger, even without continents to shape them. Tides rub energy into the ocean and coasts. The friction of that rubbing adds gentle warmth to the system and mixes the upper layers of the sea. With stronger tides and a continuous rain, mixing would have been effective. Layers rich in dissolved volcanic gases would have blended with fresher water from the sky. Chemistry would have traveled far, not just near vents or river mouths. That broad mixing is one way to understand how the ocean became quickly uniform enough for later life to find wide habitats rather than isolated pools. Many ask how the planet avoided a deep freeze if the sun was weak and clouds were thick. Part of the answer lies in that steady greenhouse blanket. Part lies in the heat still trapped in the interior, and part lies in the very nature of water. When the surface began to cool toward the freezing point, sea ice would have formed and reflected more sunlight, which should have encouraged further cooling. But as long as volcanic outgassing kept adding carbon dioxide and water vapor to the air, the greenhouse counteracted the mirror effect of ice. Also, open water around volcanoes and in places where currents concentrated warmth would have resisted complete icing. In a world of constant rain, those open patches would have acted as windows, allowing the ocean to breathe and the sky to keep its cycle moving. There is something soothing in the thought that the planet set its own pace without any need for fragile balance from the outside. The idea of a long, rainy age is not a single thunderclap in a single era, but a reminder of how feedbacks can sustain states for long periods. As long as the supply of vapor from inside the Earth continued, as long as cloud seeds remained plentiful, and as long as the radiative balance favored condensation, the rains could go on for spans that make human time feel like the blink of an eye. Evidence and models continue to refine this picture. When scientists analyze very old crystals, they search for elements that tell of low-temperature interaction with liquid water. When they model the primitive atmosphere, they compute how clouds of different thicknesses, droplet sizes, and heights would affect the planet's temperature. They test how sulfur aerosols from eruptions would seed clouds. They examine how lightning might have crackled in the thick sky, and whether it helped drive the early chemistry that set the stage for life. The beauty of the rainy age hypothesis is that it invites all these lines of inquiry into one coherent, gentle narrative. From sky to stone and back to sky again, the cycle of water is the quiet engine of our world. On the young Earth, that engine may have run with astonishing constancy, turning volcanic exhalations into clouds, and clouds into rain, and rain into oceans. The salt of the sea would have been a diary of rock dissolved one ion at a time. The earliest sediments would have been the handwriting of streams that had no banks but the edges of lava fields. The first continents were not single blocks that simply rose. They were mosaics, welded from island arcs and cooled plateaus, and every piece of that mosaic was washed and abraded by the persistent rain. Imagine standing at the shore of the first true ocean. The sky is a heavy pearl grey. The sun appears as a round pale disk, like a lantern seen through fog. The surf is steady but not violent. There are no plants on the land and no trees on any horizon. The smell is clean and mineral with a hint of sulfur. The ground is dark basalt that crunches like glass underfoot, veined with paler minerals where fluids have passed. From the inland hills comes a lace of streams. Every stream is busy cutting its youthful valley. Every small waterfall rinses fresh rock dust downstream. The scene is quiet and it feels endless, and for geologic time it almost is. As the era of relentless rain softened, the world did not become dry. Rather, it graduated into the pattern we recognize today, with pockets of aridity and belts of moisture, with monsoon rhythms and ice ages, with deserts and rainforests. The long lesson of those early millions of years remained written in stone and sea. Oceans had formed deep basins where currents could work their slow spell. Continental crust had thickened and lightened, creating higher ground that would one day host rivers and lakes of many moods. The atmosphere had thinned and cleared enough to let blue skies shine between clouds. Yet in every cloud and every drop, the memory of that first long rain remained, a kind of ancestral rhythm within the hydrological cycle. When we listen at night to steady rain on a window, we are hearing a very ancient song. It is the same song that may have helped cool the earth to a livable temperature, that salted the seas, that delivered trace metals into solution and then into clays, and that polished the early crust. Whether the unbroken symphony lasted 20 million years or closer to 30 is almost a footnote compared to the meaning of the melody itself. The planet found a way, through simple physics and patient feedbacks, to turn a fiery beginning into a blue, life-capable home. And it did so not with cataclysms alone, but with the soft, repeated touch of raindrops. Imagine the young planet wrapped in cloud and steam, its skin still warm from the deep interior, its skies never drawing a clear breath. In this world, the atmosphere does not simply sit above the surface like a cap. It moves as a slow but relentless conveyor, a planet-sized circulation that lifts water vapor from the near-boiling seas and returns it as rain without pause. Near the equator, the rising branch of this vast cell swells with heat. Towering cloud canyons reach very high, their tops spreading like cold shields that glide toward the poles. High aloft, the air cools and dries, then sinks and warms again over the subtropics before sweeping back along the surface to the equatorial cauldron. With the continents tiny or absent, nothing interrupts these belts. Entire oceans lie under broad rain bands far wider than the modern intertropical convergence zone. The result is a slow and steady heartbeat. Warm surface water evaporates, rises, condenses, and falls back in sheets day after day, year after year, until the rhythm itself becomes part of the geology. Where the rising branches meet descending air near the poles, the difference in temperature wrings even more water from the sky. The planet breathes, and with each breath, a little more of the mantle's exhaled water becomes the first true ocean. Seen from space, this ocean is not entirely blue. A soft brightness veils the globe. Above the steaming surface floats a second ocean, an ocean of cloud. The droplets in these clouds are not like the droplets we know today. When the air is overly rich in water vapor and the temperature is high, water can slip into a state that is neither a usual gas nor a usual liquid. In this near-critical realm, droplets behave strangely, coalescing and splitting with ease. Add to this chemistry the faint light of the early sun and a constant rain of fine particles from volcanoes, and the planet gains a crown of haze. Methane bubbling from the warm crust meets sunlight and lightning and turns into long-chain organics that clump into tiny grains. They hang in the upper air as a photochemical veil. It is thin enough to let blue light pass, thick enough to scatter and soften the day. At sunset, the veil glows with copper and violet, and at night it dims the stars. The surface sees fewer harsh shadows. Even the ocean looks different, its skin covered in transient films of oily hydrocarbons and sulfur compounds born from the deep. These films dampen capillary waves and make the young seas appear unnervingly smooth between storms. In the unending cloud, the sky speaks with electricity. Lightning stalks the convective towers like a restless animal pacing its territory. The bolts are frequent because the updrafts are powerful and the air is always saturated. Every minute, charge builds as ice crystals and larger graupel collide and separate. Every minute, the imbalance seeks a path to ground or to another cloud. Each white vein of light punches nitrogen into a state that can react with oxygen and water. The result is a gentle rain of nitrates that settle into ponds, trickles, and the open ocean. In effect, the storm is a planetary chemistry set, carving a doorway into the stubborn nitrogen molecule and handing the newborn ocean the first packets of bioavailable fertilizer. Thunder follows with a rolling voice that lasts far longer than we hear in modern storms because the cloud towers are so tall. Some flashes ripple sideways for many tens of kilometers inside the cloud and never show themselves outside. Their sound is a deep groan that seems to come from everywhere at once, with rain as a chisel and meteoric debris already cracked by thermal shock. The surface begins to rearrange itself. Where warm, buoyant parts of the early crust thicken, they rise as scattered protocontinents. The word continent is generous. These are lumpy rafts of lighter rock, draped in rubble and soot, stitched together from volcanic flows and pumice. They are besieged by storms. Water tumbles off them in braided torrents that polish stones into pebbles and grind pebbles into sand. The smallest grains wind up far from their birthplace, carried down steep slopes to the ocean fringe where they settle into fans. In time, these fans weld onto the rafts as they cool. As the cycle repeats, small shields of durable rock begin to appear, made not by quiet uplift, but by the tireless work of rain. They are the first pages of the rock record that speak clearly of a hydrologic world. Under this raw landscape works the skeleton of the ocean. The mantle convects like a slow pot, and where hot material rises, the seafloor tears open along serpentine ridges. Basalt wells up, chills, cracks, and becomes the crust. In a world awash, the newborn crust is immediately attacked by water that seeps into its fractures. The ridges are not pure lines, but a broken necklace of segments, each with its own heat flow and volcanic rhythm. Off-axis, the crust sags, grows heavier, and fractures again. Water circulates through this entire framework, not just in tiny veins, but in channels large enough to drive steady currents. The ocean, then, is not only on top of the crust, it is inside the crust, filling its pores and faults and acting as both coolant and courier. When seawater meets the ultramafic rocks of the deeper crust and upper mantle, a quiet alchemy begins. The magnesium and iron-rich minerals take up water and change into a new suite of green and dark rocks. This reaction, called serpentinization, produces heat and hydrogen. The heat keeps the reaction going. The hydrogen bubbles up and meets carbon-bearing fluids, sometimes making methane and longer hydrocarbons. The chemistry rewrites the water as it moves, stripping it of some ingredients and gifting it others. In the warm places, the fluid emerges loaded with dissolved metals. In the very hot places, it flashes into black smoke as it hits cold seawater, and the metals precipitate as fine grains of sulfide. In the cooler places, the water rises as clear, shimmering plumes that are alkaline and rich in hydrogen. Both kinds of springs carve chimneys out of their own mineral harvests, building fragile towers and gardens in the dark. Around these vents, a different kind of weather takes hold. It is a weather of chemistry rather than air. Gradients of temperature and pH drape the sea floor like invisible curtains. Where one curtain crosses another, energy becomes available for molecules to climb into more complex forms. Iron and nickel in the rocks behave like primitive catalysts. Porous minerals such as clays and carbonates offer microrooms where molecules collect and try new arrangements. If you could shrink yourself and drift through one of these systems, you would feel like a seed riding a warm mist through a honeycomb of tiny chambers. The rain from above never reaches this place directly, yet it powers it indirectly by maintaining the ocean that keeps circulation running. In this sense, the deluge sky is an angel investor in the chemistry of the deep. Through all of this, the planet must keep its temperature in a livable range. The sun is weak by a significant fraction compared to its future strength, and yet the rain-soaked Earth does not freeze into a permanent white mirror. Carbon dioxide, released in copious amounts by the young volcanoes, thickens the atmosphere and traps heat that would otherwise leach away to space. Water vapor joins in as a potent greenhouse gas, but water vapor alone would never be enough because it condenses too easily. Carbon dioxide provides the floor heating, and water adds the blankets. Methane produced in the crust, and perhaps by nascent life, adds another layer. The balance is delicate. Too much greenhouse gas would boil the ocean, too little and the world would crystallize. It is as if the planet finds a comfortable hollowness in the middle of the possible, and the endless rain is a symptom of that sweet spot. Yet carbon dioxide is not free to accumulate without limit. The same rain that fills rivers and oceans also attacks rocks, especially fresh volcanic rocks rich in calcium and magnesium. The droplets pull a little carbon dioxide from the air as they fall. On the ground, they become weak carbonic acid that extracts metal ions from the stone. These ions ride rivers to the sea where they settle with carbonate to form new minerals. In doing so, they lock away the carbon. Over very long spans, this slow weathering and burial set up a thermostat. If the world warms and rains harder, weathering speeds up and more carbon is removed from the air. If the world cools and rains less, weathering slows. Carbon dioxide from volcanoes accumulates and the air warms again. The dial is not quick. The dial turns over many tens of thousands or hundreds of thousands of years. But when you are imagining a rain age that lasts many millions, the slow dial matters. It means the planet can self-tune and avoid the two extremes of runaway heat and perpetual ice. Even so, there are hints that the long deluge might have blinked now and then. The sedimentary record that would tell us this story is nearly erased by later recycling of the crust, yet a few clues survive. Some very ancient zircons, tiny crystals that act like time capsules, carry oxygen isotopes, suggesting that liquid water interacted with the crust very early, perhaps even before the most intense rains had begun. Other clues from later eras show that the planet flirted with snowball states when ice tried to reach the equator. These were probably much later than our rain age, but they reveal that the global thermostat sometimes overshoots and sometimes undershoots. In the context of the deluge era, one can imagine brief intervals when volcanic activity paused in a region or when the distribution of clouds shifted, allowing a chill to deepen. The rain would not cease, but it might lighten, and high valleys on a tiny continent could briefly hold ice. Then the interior would exhale again, greenhouse gases would build, and the warm conveyor would resume its full strength. In this world of ceaseless downpour, the noise would be different from any modern storm soundscape. It would be a constant broad hiss, somewhere between surf and distant applause, punctuated by the low roll of thunder that sometimes lasted for many minutes. The sea would not rest. Fetches of wind would extend for thousands of kilometers without land to break them. So swell would circle the globe and meet itself again, interfering in gentle and then in violent ways. At times the ocean would appear calm, a glass skin under a bruised sky. At other times, long low rollers would plod across entire basins, only to rise and trip when they ran onto the shallow flanks of a volcanic plateau. The air itself would feel heavier on the skin because warm air can carry so much water. Even between showers, a pedestrian of that ancient shore would feel slightly damp all the time, as if the planet were wrapped in a soft, wet shawl. Lightning made not only nitrate, it also welded sand into little glassy tubes called fulgurites and scoured dunes into strange sculptures. The constant drizzle far from the storm bands carved pollen-free river deltas, whose geometry depended solely on physics and not on vegetation. Without roots to hold soil in place, rain gullies braided and unbraided with every season. Yet there were seasons of a sort, because even a largely ocean-covered Earth still leaned on its axis and still orbited the sun. Monsoon-like shifts likely moved the thickest rain belts north and south over the year, writing a quiet cadence into the noise. In warm years, the belts drifted farther. In cool years, they retreated. The emerging continents altered the script as they grew. Their presence broke the simple symmetry of the atmospheric conveyor. Mountains forced moist air upwards, wringing extra rain on windward slopes and leaving lees of relative dryness that could never truly dry. Rivers learned the shapes of these new ridges and explored the most efficient lines to the sea. Where several rivers met a shallow embayment, they built deltas whose tops were constantly renewed by storms. Between these deltas lay lagoons that sometimes turned briny as evaporation outpaced replenishment. When the next long storm season arrived, those lagoons spilled like bowls and flushed their salts back into the open ocean. Slowly, the sea took on the taste we now recognize. Meanwhile, the seafloor conveyor persisted. At young ridges, sheets of pillow basalt erupted into the water, each pillow cooling in seconds to a skin of black glass. Beneath, the still hot interior cracked and allowed more water in. In some places, the crust was thin enough for deep faults to reach far down. Through these cracks, heat and chemical energy poured into the water and made fountains of minerals that, in time, stiffened into chimneys. Around the chimneys clustered communities that fed not on sunlight but on chemistry. They harvested hydrogen and methane and sulfide. They made organic molecules from carbon dioxide in the same way plants do, but the energy came from the redox gradients in the vent fluids rather than from photons. In this sense, the endless rain above acted as a distant ceiling that embraced a world of darkness blooming with unexpected gardens. If we step back and look at the globe as a system, the image is one of balance through motion. Rain does not merely add water to the surface, it powers weathering, which tunes the climate. It feeds rivers, which carry ions to the sea and gradually construct a salty ocean. It smooths high ground and infills low basins, guiding the growth of early continents. It interacts with a restless crust, which in turn releases gases that keep the air warm enough for rain to continue. It encourages electrical storms that donate nitrogen to the ocean's pantry. Through each of these threads, the long downpour acts as both sculptor and teacher. It teaches the young planet how to become a world that can support chemistry of increasing complexity. There may have been brief windows when the rain slackened, perhaps during lulls in volcanic outgassing or during times when continental fragments shifted into positions that altered the flow of heat and moisture. During these pauses, thin skins of ice could have formed at high latitudes or even at sea level in shaded basins. But as the mantle simmered and degassed anew, as fresh basalt spread at ridges, as methane seeped from the altered rocks, the warm greenhouse would return and the clouds would once again draw together. The long narrative resumes. The planet continues to pour from sky to sea and from sea to crust and back again. In the middle of this story, if you stood on a black sand strand and watched the horizon, you might notice a change too slow to name. The horizon would move inland a little less often. The sea would linger where it was, as if it had finally met a bowl big enough to hold it. The sound of rain would be the same, but the shape of the coast would begin to persist from season to season. In that persistence lies the threshold. The world of rain without oceans yields to the world where oceans can exist even when the rain briefly relents. From then on, the sky remains a partner rather than a sole architect. The age of unbroken downpour has done its work. It has written rivers on bare rock, salted the sea, tempered the climate, charged the deep with chemical power, and set the stage for the next act in which the planet entertains the possibility of life. The longer the rains fell, the more the planet began to sort its chemistry into gentle gradients. Seawater was not a single flavor of salt, but a layered recipe that changed with every trickle from the newborn continents and every pulse from the seafloor. Sodium came readily from weathered feldspar. Chlorine rode out of volcanic gas as hydrochloric acid, was tamed by rock and took its place beside sodium. Calcium and magnesium seeped from basalts and peridotite and in turn met dissolved carbon dioxide to make temporary shells of carbonate that drifted and redissolved. Silica wandered in quiet abundance, the ghost of volcanic glass softened by ceaseless showers. In this broth, the rules of solubility and the rhythms of rain wrote the first patient inventories of the ocean. Even the color of the water shifted with its chemistry. With little oxygen to stain it blue from the surface, iron wandered as a soluble greenish partner and only occasionally met enough oxidants to fall out as a whisper of red. On the young coasts, clay was the subtle architect that rain summoned from stone. Every raindrop that struck a feldspar grain offered up aluminum and silicon and potassium and then urged them to reorganize into sheets as thin as thought. These clay laminae could adsorb ions, cradle organic molecules, and present a patchwork of charged surfaces. They were shelves in a chemistry library whose books were molecules that stuck for a while, moved and reacted. Rain made the shelves and turned the pages. Clay minerals favored certain orientations, protected fragile chains, and sometimes even templated simple repeating patterns. When warm pools along volcanic slopes dried between cloudbursts, clay concentrated what the water offered and then, as the next storm returned, released the inventory into new mixtures. The cycle of wetting and drying, even within a world that rained almost without pause, was created by hot ground, steaming fumaroles, and brief lulls beneath thick clouds. In those moments, a strand could lengthen by a few units. In the next shower, it could fold, hide in a clay nook, and wait for the next chance. From the sky came gifts older than the planet's crust. Carbon-rich meteorites fell into the warm sea and into crater lakes. Many carried aminated acids, ringed heterocycles, simple alcohols, and sticky tars. The rains scoured the impact gardens and smuggled that cargo down gullies into lagoons. The ratio of heavy to light hydrogen in these organics differed from the water's own ratio, a quiet signature that showed up later in the record of ancient rocks. These deliveries did not have to be large to matter. A thin smear of molecules over a square kilometer of mudflat could be concentrated 1,000-fold by evaporation where a hot spring licked the shore. Lightning within the perpetual cloud deck added its own share to the pantry. Every flash jostled nitrogen, split it, and let it recombine into nitrites and small amounts of ammonia. In a world without soils and plants, the air itself became a factory for fixed nitrogen, and rain was the courier. Ultraviolet light, so often cast only as a hazard, found narrow windows through the global overcast. Water vapor and carbon dioxide ate part of the spectrum, but gaps remained, especially when ash and hazes thinned. In those moments, shallow pools turned into light-powered benches. Certain reactions that stall in the dark leap forward under ultraviolet, forming sugars from smaller fragments, energizing phosphate groups, or pushing simple nucleotides toward short chains. Under a constant drizzle, surfaces remained clean and reactive. Mineral veins of zinc sulfide and iron sulfide acted as photochemical diodes. They guided charge, helped select handness in organic building blocks, and kept fragile intermediates from falling back to chaos. Tides, though gentle compared with the storms above, still breathed across the shores because the new moon already tugged at the planet. Twice each day, water rose and fell, even under the endless rain, where hydrothermal streams met the sea, where waves nudged warm pools behind basalt sills. Cycles were drawn by gravity rather than sunshine. Wet and dry followed one another on a schedule that molecules could learn. Polymers that only lengthen when nearly dry found their moments at the top of the tide. Vesicles of fatty acids that fall apart in pure water but hold together in brines collected in saltier puddles and survived long enough to trap catalysts. The rain made everything slippery. The tides made it rhythmic. The earliest footprints of rainfall preserved in stone are not literal. No animal walked those shores, but there are clues in the geometry of certain ancient sediments. In a few rare outcrops, fine beds show the dimples and ripples of drops large enough to have fallen from thick clouds. Elsewhere, layers of silt are organized into couplets that speak of beds laid down by repeated pulses of floodwater. The chemistry of old zircons holds more precise testimony. Their oxygen isotope ratios suggest that liquid water interacted with continental crust very early, which requires rains and rivers to have cycled continuously over scales of thousands of seasons. Not every geologist agrees on how to read these tiny registers. Yet the weight of evidence leans toward a world where clouds kept the sky busy. Silica-rich terraces at the mouths of hot springs were another script, even in a drowning climate where every surface glistened. Vents wrote mineral pages as hot, silica-laden waters met cooler pools. They built spongy ledges that trapped bubbles and fibers. As they grew, the ledges created new flow paths, so channels wandered and braided. Within the pores of silica sinter and in the slick films of iron hydroxides, tiny hollow spheres and filaments sometimes self-assembled. Later ages would host microbial communities that carved those same textures into living rock. Whether the earliest examples were purely chemical or already carried a faint biological intention is debated. The important point is that rain delivered reactants, controlled dilution, and kept the surfaces renewing. The ocean at this stage was not yet blue in the oxygenic sense. Iron poured in from mid-ocean ridges and from weathered bay salts and remained dissolved in the absence of much free oxygen. Whenever an island arc pushed above the sea and offered a perch for photochemical reactions that created local oxidants, plumes of iron swiftly fell as fine layers of rust. These transient events left banded layers here and there, the earliest whispers of the grand iron formations that would arrive far later. In the rain epoch, such deposits were more like punctuation in a long, watery sentence. Metabolisms that do not need oxygen fit this world like tools made for a single hand. On the flanks of black smokers and in warm alkaline vents, gradients of temperature, pH, and redox stacked like layers of music. Hydrogen produced by serpentinization met carbon dioxide to drive the creation of simple organics on mineral catalysts. Formate and acetate trickled into surrounding fluids. Sulfur species shuttled electrons as if passing notes in a quiet conversation. It is a plausible stage where life could have learned to harvest chemical potential and to enclose the harvest inside membranes. Whether that happened in this era or later remains contested, yet the rain nourished the networks. Constant dilution prevented poisons from accumulating and helped successful arrangements spread along the sea floor. As oceans deepened, their surfaces smoothed and their cloud cover gradually thinned. The planet shifted from a world where rainfall wrote everything to a world where the water cycle found a quieter balance. Volcanic outgassing slowed as the crust thickened. Silicate weathering subtly accelerated because more land had lifted above sea level. Carbon dioxide, once the heavy quilt that warmed the infant world, was slowly folded and tucked into carbonates and buried in the crust. The greenhouse boundary moved just enough to permit longer, clear spells between showers. Not cessation, but cadence. Thunder still rolled. Storms still paraded. But an ocean planet with ragged archipelagos and a sky of moving lanes replaced the almost unbroken grey. In this maturing climate, salt budgets found their set points. Rivers carried a constant trickle of dissolved ions. Hydrothermal systems at mid-ocean ridges traded magnesium for calcium and locked some components into newly formed basalts while releasing others. Evaporation in warm belts thickened local brines and led to small basins where salts briefly crystallized and were churned back into the sea by new rains. The average salinity sought a moving compromise between inputs and sinks. That compromise leaned toward values not very different from the modern sea, although the exact number wandered with time. What mattered most for the chemistry of life was that the ocean retained a moderate ionic strength that stabilized membranes and supported proton gradients across thin walls. Shorelines subtly changed their character once true continents began to grow thicker roots. Granite magmas rose, cooled, and birthed lighter crust that stood higher above the sea. Sprays of island arcs fused, sutured, and formed broader blocks. Rivers lengthened, floodplains appeared, deltas built their crenellated maps. The rain, now falling on more extensive land, carved dendritic patterns and delivered fine loads of clay far offshore. As sediment blankets thickened, they pressed earlier beds into stone. The sprightly cycle of the first archipelago world gave way to more organized basins where long-term stratigraphy could accumulate. With it came new settings for cycling organic molecules through drying and wetting, new estuaries of variable salinity, and new sheltered pools that might host precursors of cells. Lightning remained a daily author of nitrogen chemistry, but it no longer ruled alone. Subduction zones began to breathe nitrates into the ocean through hydrothermal outlets. Volcanic plumes oxidized some nitrogen species and reduced others in rapid succession, making a palette that submarine communities could exploit. The sky opened more often to stars. With clearer nights, the surface ocean occasionally cooled enough that mist formed and drifted, then dissolved at dawn into pale rains that felt less like a deluge and more like weather. The end of the long rain epoch is not a singular moment. It is a palette of transitions spread over millions upon millions of years. The geometry of the carbon cycle reached a new equilibrium. The young sun brightened by a small but important fraction, easing the need for a thick greenhouse blanket. The planet's spin slowed just a touch under the drag of tides, and days lengthened, changing how energy was distributed between day and night. The global Hadley cells that once wrapped the world from equator to pole loosened into bands that resemble the modern circulation. Precipitation became more zonal, with rainy belts and drier corridors, with monsoon-like pulses near growing continents and steadier mid-ocean showers. The story of rain transformed from a constant chapter to a recurring theme, and under that calmer schedule, life, if it had already begun, found new ways to test itself if it had not yet begun. The calmer schedule offered settings where fragile assemblies could persist long enough to evolve error correction. In tide pools and vent fields, in porous basalts and silica sponges, in films upon clay, and in the sheaths of iron hydroxide, autocatalytic cycles gained companions. Membranes learned to keep gradients even while rain and tides worked to wash them away. Small networks of reactions that drew energy from hydrogen or from ultraviolet light began to depend on minerals they had themselves altered. The planet had turned from a stage for chemistry into a partner. The rains did not stop. They simply learned to sing in time. When they had been nearly constant, they carved the basins, set the salinity, fed the vents, and painted the first terraces of silica. When they modulated, they gave rhythm to shores and to cycles of concentration. All the while, the ocean thickened from a glaze into a deep library. By the time clouds finally yielded to blue, more often than not, our world held seas that could, host continents of chemistry and, perhaps, groups of cells. Much later still, oxygen would rise, ice would sometimes take hold on a global scale and then retreat. Continents would dance their slow dance. But the first credo of the surface was written by rain, long and patient. It solved the contradiction of a faint young sun and a warm sea. It chose which ions would dominate the recipe of water. It wrapped geology in a skin of dissolution and transport, and it left across the ageless cratons the taste of its careful work. The oldest rain gauges left by the deep past are not metal cylinders or glass flasks, but tiny crystals that learned to keep a diary. In their lattices, the ratio of heavy oxygen to its lighter sibling drifts with each step of condensation and each mile of cloud travel. When water vapor cools and turns to drops, the lighter isotope prefers the sky while the heavier one moves with the falling rain. In a world of endless precipitation, that sorting would have been relentless, a planetary scale distillation column dripping day after day. The ancient zircons from the old hills in the west of a southern continent show just such patterns. Some of them formed little more than 4 billion years ago, yet they hold oxygen ratios that suggest liquid water touched the surface and kept touching it for a very long time. If you imagine these crystals sleeping inside volcanic rocks while storms passed overhead without pause, you begin to sense how isotopes became a memory of weather, compact and nearly immortal. The same logic applies to hydrogen. Water is not a single substance, but a family of twins, one with the lightest hydrogen and one with the slightly heavier form called deuterium. Each stage of evaporation and rain nudges the family balance. If the air is forever condensing and falling, the oceans trend toward one fingerprint, the clouds toward another. Meteorites carry yet another signature, frozen in the cold before any world had an ocean. By comparing all of these, geochemists trace the whisper of supplies from the deep interior and from space, and the long breath of the atmosphere as it rained and re-rained. The ocean that finally settled may have started with a deuterium to hydrogen ratio. Not far from what we measure today, but the path to that modern value reads like a palimpsest of countless downpours. Where rain meets rock, rivers are born, and where rivers run, they chew mountains into dust. The dust tells the tale in strontium, calcium, and neodymium. Young volcanic crust weathers to release one flavor of strontium. Ancient continental blocks release another. In sediments of great age, the gradual swing of these isotopes looks like a dim tide line marking the slow assembly of the first broad shields. During an age of continuous rain, weathering would have been an almost surgical art, water probing every crack, dissolving feldspar into clay, and ferrying ions to the sea. The banded iron layers that later settled on the sea floor likely needed such a steady conveyor. Iron flowed in from the land and from the hot springs along the spreading ridges, met the new oxygen from early photosynthesizers or the oxidizing power of UV-struck peroxides, and fell out of solution in thin, patient sheets. Pages in a book written with rust. Clouds under such conditions were not random puffs. They were architecture. The planet likely ran with broad belts of ascent where warm, wet air rose every day, and flanking bands where dry air sank only to be reloaded by evaporation and pushed back toward the rising lanes. Imagine a global monsoon with equatorial supercells taller than mountains, anvils that met each other to close the sky, and nighttime thunderstorms that never truly ended. Because dawn elsewhere kept the engine spinning, the small crystals of aerosols seeded the drops. Volcanic ash, sea salt, and the haze from photochemical reactions gave each droplet its starting point. When aerosol sources surged, clouds became brighter and longer lived, bouncing sunlight back to space and trimming the heat that reached the surface. When aerosol sources waned, drops grew larger, fell sooner, and clouds cleared just enough to warm the ocean beneath. In this slow dance, the rain sustained itself not as a single storm, but as a planetary habit. Amid the roaring sky, there were pauses so brief the rocks barely remember them. In a young world spinning under a fainter sun, a burst of volcanic sulfate could brighten the planet enough to tip warm rain toward chill mist. Ice might edge from high elevations or high latitudes out across the shorelines, then retreat when carbon dioxide rallied from volcanoes and from the slow release of oceanic bicarbonate. The paradox of a faint young sun not freezing the world finds its truce in these counterbalancing flows. Greenhouse gases caught just enough heat, clouds reflected just enough light, and the ocean spread as a heat-bearing quilt, trading energy between equator and pole. The rain did not stop. It simply changed costume for a while, spitting sleet in some places, fog in others, liquid sheets elsewhere, then returned dressed as thunder again. The saltiness of the oceans carries the arithmetic of this long campaign. Sodium and chloride both have parents in crust and mantle. Rivers carried them down in steady millions of tons each year, and hydrothermal vents returned some to the deep in other forms. In a planet of ceaseless downpour, that river budget would have been larger, the pipelines fuller. What we sip in a modern mouthful of seawater is the result of an ancient tug of war between input and removal mechanisms that reached a kind of calm balance only after a few 100 million years. The taste of the sea is an echo of rain. Behind the rain stood volcanoes breathing, outgassing from the mantle did not come in a single gust, but in pulses from lines of vents, from flood basalts, from island arcs hugging subduction zones that were just learning to walk. Each eruption lifted new water into the sky. Each degassing also contributed carbon dioxide and sulfur dioxide. In the short term, sulfur made reflective aerosols that cooled the surface, disfavoring evaporation. In the long term, carbon dioxide nourished the greenhouse, siding with water vapor to keep oceans liquid under the faint sun. This alternating input likely helped anchor the planet in a stable corridor where rain could continue without freezing the surface or boiling it dry. Comets did visit, and so did asteroids. They offered water and organics, but they also delivered heat. When a large body meets an ocean, the surface can flash to vapor, a temporary steamy exile of the sea. Yet gravity and cold night skies condense the steam back into drops. Each impact punctuates the long symphony of rain with a drum roll, but the melody resumes. The heavy hydrogen ratio in some comets sits a little above the ocean's value, making them only partial donors. Many carbonaceous asteroids match better, sharing a deuterium balance that looks more like the water already here. The sky, the sea, and the stones negotiated their shares without keeping minutes, leaving us to infer the meeting from the chemistry scrawled in mineral margins. All the while, the magnetic field helped keep the ledger honest. A working core dynamo wrapped the planet in lines of force that turned the solar wind aside. where the wind touches atmosphere without such protection, as on the neighbor that is now dry and hot, the upper air can escape molecule by molecule into space. Early Earth did lose hydrogen from the high thermosphere, but the field held the loss to a trickle rather than a flood. The rain cycle stayed mostly a closed loop within the gravity well, not an open drain to the void. Tides from the newly established moon needed the growing ocean. They stirred shallow basins and lit up the coastal shallows with mixing. That energy helped bring nutrients to surface waters and drove estuarine flows that cut early deltas into crescents of sand. Even in an overcast world, tides wrote their schedule into near-shore currents. Much later, ripple marks in ancient sandstones would record symmetry and spacing typical of regular tidal motion. In those faint grooves, you can read a message from a sky you cannot see. Under the cloud cap, the photochemical laboratory in the upper atmosphere kept working. Methane from serpentinized rocks and from any early microbial methanogenesis could form a golden haze when sunlight broke its bonds. Such haze reflects light, cools the lower atmosphere, and scatters ultraviolet into a softer blue. In moderation, it protects. In excess, it chills. The rain colony below would modulate the haze by oxidizing methane with radicals born in lightning and by burying carbon as carbonate in new sediments. The whole sky became an active membrane, transforming volcanic gases into raindrops and raindrops into river fuel. Field geologists searching for the footprints of this age look for specific textures. Conglomerates with rounded pebbles show that liquid water rolled stones for long distances. Mudstones laminated in thin, even sheets hint at calm settling from suspension during long, wet seasons. Clay minerals such as smectite and kaolinite betray intense chemical weathering, the kind that eats feldspar to its skeleton. Even in terrains reworked by later heat and pressure, some of these signatures persist, like a watercolor that keeps its mood after many hands have handled it. From those landscapes, the first terrains of low relief arose, the proto-deltas and wide floodplains where rivers split into multiple channels and laid down bars of sand that shifted, merged, and were replaced. In such wandering, you get swamps and oxbow lakes, stagnant backwaters lined with microbial mats. You can picture a world where the sound of rain on water was more common than rain on stone, where lightning walked along the cloud base like a slow spider, and thunder was the constant percussion under which chemistry rehearsed its themes. Across that saturated surface, the ocean acted as a battery. At alkaline vents, porous minerals formed tiny chambers separated by thin walls peppered with iron and nickel. On one side of each wall, the water held more protons. On the other side, it held fewer. The difference in proton activity became a force that could coax simple molecules into strings, then sheets, then assemblies that could harvest the gradient and feed on it. In this view, metabolism starts as a way to ride a natural electrical slope. Rain helps by supplying carbon and nitrogen to these vents, washing them in a solution of possibilities day after day, century after century. Not every part of the ocean was equal in promise. Shallow basins caught sunlight even when clouds thinned for a short while, and they exchanged gases with the sky much faster than the deep. But the deep welcomed hydrothermal gardens, rich in metal catalysts and safe from ultraviolet spikes. Some origin stories seat the first protocells in warm ponds where evaporation concentrates solutes between rainfalls. Others set them in vent pores where concentration happens in the tiny maze of rock. A long rain scenario allows both laboratories to operate, sometimes together when runoff carries pond experiments to sea. The chemistry of early seas paints itself in the iron formations mentioned before and also in the sulfur story. Sulfur in sediments shows odd fractionation signatures that occur when ultraviolet light breaks sulfur dioxide in the absence of much oxygen. If those mass-independent patterns dominate for a long time, it hints that the air remained low in oxygen while rain and lightning were abundant. Later, as life learned to split water and release oxygen, the signature fades. The timing of that fade tells us when the sky took a new path. Before that shift, rain ruled the nutrient cycles. After it, oxygen joined as a new engineer of climate and weathering. Modern climate models try to test the plausibility of a long, wet epoch by recreating a slow-spinning, cloud-rich world under a dimmer sun and feeding it volcanic gases consistent with a hotter mantle. They simulate convective towers that top out at heights few planes now reach, and tropical belts that are wider and stronger. In those experiments, rain does become a nearly continuous global habit when key parameters line up. On the other hand, the models also show that if clouds grow too efficient at reflecting sunlight, global chill follows. The most probable path lies between these extremes, with broad latitudinal stripes where rain rarely ceased and other belts where showers pulsed with a longer rhythm. Planetary brightness matters. A world wrapped in bright clouds reflects much of the incoming light. A dark ocean absorbs most of what reaches it. Regions of foam and spray flicker between these two extremes, changing the budget minute by minute. Over millions of years, the average is what counts, and that average was likely set by the ratio of greenhouse gases to cloud cover. Too much bright haze and you build a mirror that cools. Too little and you risk a greenhouse that steams. The successful outcome that Earth enjoyed implies a slow autopilot of negative feedbacks. Silicate weathering accelerates when it is warm and wet, drawing carbon dioxide down. When it is cool and dry, it slows, leaving more carbon dioxide to rebuild the blanket. The long rain fit within that regulator like a needle within a groove. The water did not evaporate away because it pooled in a deep enough basin with a strong enough gravity well under a sky protected by a magnetic hood and tempered by the greenhouse. It did not freeze solid because volcanic fires and oceanic heat transport, helped by tides, kept moving energy from sunward to poleward. In that dynamic balance, the rain learned patience. Meanwhile, the crust below the sea learned to recycle itself. At spreading ridges, hot rock rose and released volatiles, then cooled to basalt. At weak zones, it dived again, dragging soaked minerals downward. Each pass of such a conveyor supplies water back to the mantle and fresh volatiles back to the air. The two cycles feed each other, the tectonic and the hydrologic, and in their feedbacks, the long storm finds a mechanical ally. Stones literally drank rain and later breathed it out as steam. When scientists date these episodes, they count atoms in the minerals that survived the tempest. Uranium slowly becomes lead at a rate the universe keeps, and the ratio of parent to daughter acts as a watch. Some zircons are older than 4 billion years, yet their chemistry requires liquid water at the moment they crystallized. These are not photographs, but they are thoughtful sketches, more precise with every study. Among the oldest structures, thin domes and wrinkles in ancient sandstones and cherts may be the remains of microbial mats. They look like the forms that modern mats leave on tidal flats, just scaled to another epoch. If they truly are biosignatures, they prove that life learned to build cities while rain still wrote the weather report. The mats would have loved the nitrate sparked by lightning and the steady supply of phosphorus and iron from rivers. Under a panting sky, they might have farmed sunlight in occasional clearings or grazed on chemical gradients in the twilight of shallow lagoons. Lightning itself was a silent patron. Every flash breaks nitrogen molecules and lets them meet oxygen to form nitrate. Rain then delivers those nutrients to surface waters and soils. In the age of storm, this fertilizer factory supplied a planet-scale subsidy, bridging the gap until microbes evolved their own nitrogen fixation machinery. If you listen to a distant thunderstorm and count the seconds to the next flash, you are hearing an ancient economy tallying its credits. This is how an imagined epoch of long rain can be made to sit within physics and chemistry. It weaves isotopes, minerals, clouds, volcanoes, impacts, tides, and electric sparks into a patient climate. In that patience, water turned from breath to drop, from drop to stream, from stream to sea, and from sea to solvent and stage. All later weather, from gentle drizzle on a garden to the calm snow over a polar cap, is an afterword to that opening chapter. The rain had already rewritten the chemistry of the planet by the time the first flickers of biological oxygen appeared. Oceans that were once thick with dissolved iron grew less hungry for electrons as rivers kept bringing a steady cargo of bicarbonate and trace metals from the altered crust. In that warm, continual drizzle, salts found their way into the water column in ratios that would look familiar even today. Sodium and chlorine flowed from freshly fractured basalts. Magnesium and calcium joined from the weathering of olivine and plagioclase, while silica filled the spaces in between as a transparent ghost of stone. Into this increasingly conductive brine, early microbial communities tested pigments. Sunlight that pierced the cloud deck on rare luminous days found mats at the surface and at the edges of hydrothermal fields. There, chlorophyll-like molecules learned to shuttle electrons. Oxygen didn't bloom at once, but rain prepared the stage with an ocean that buffered acidity, delivered phosphorus and trace iron, and kept temperatures high enough for reactions to proceed. When the great oxygenation finally arrived long after this rainy era, it was not a bolt from the blue. It was a slow unfurling on a stage that water and weather had already built and furnished. Thinking beyond our world helps the imagination hold the scale of such a climate. Astronomers now catalogue planets where water may not be a thin veneer, but an abyssal identity. Some of those are super-Earths with gravities strong enough to keep atmospheres dense and oceans deep beyond any terrestrial analogue. The youthful Earth, during its long wet chapter, offers a laboratory in the mind for these other shores. A world wrapped in a thick envelope of steam and cloud would reflect much of its star yet trap heat with greenhouse gases. Days would be short on blue light and long on infrared glow, a spectrum where water vapor and carbon dioxide converse constantly. Wind would organize into persistent belts and storms that never fully quit. If we ever read the spectra of those distant waters and see methane hazes or heavy cloud decks, we may be seeing echoes of our own primeval weather. What our planet survived then becomes an instruction manual for others, reminding us that oceans can be born from patience, not only from comets or single cataclysms. Was the deluge truly without pause? Even a world set on constant condensation breathes in cycles. Volcanic episodes would spike the sky with aerosols and change the radiative balance for a while. The brightness of the young star would wander just enough to modulate the global thermostat. Periods more generous with sunlight might have carved brief windows when rainfall slackened from incessant to simply frequent. In those windows, crust would dry at the surface, salts would crust over and crack, and the energy of sunlight would reach a little deeper into shallow basins. Then gases from new fissures would darken the sky again, and the planet would slip back under the soft drum of continuous rain. The long record in ancient zircons and sediments looks smeared rather than discrete, the signature of a climate that did not flip between two states but pulsed around a rainy mean. Over this ocean of time, fog and low clouds became gatekeepers of planetary heat. Above the water rose a boundary layer thick with droplets that had not yet learned to fall, a world of mists drifting just above the surface. The mists reflected sunlight efficiently, especially when seeded by volcanic sulfates or breaking wave spray that lofted salt particles. At night, those same mists acted as a blanket, radiating slowly and limiting heat loss. The daily dance of haze, stratified cloud, and rain curtain became the metronome of the energy budget. Where cold, upwelling currents reached the surface, fogs would be at their densest, throwing brilliant white back into space when the clouds thinned enough for the star to find them. Where warm currents circulated, low clouds would be patchy and the sea would drink more light. Even without continents as we know them, this mosaic of optical states made the planet less uniform than the phrase water world suggests. At some point, the planet learned a new rhythm. Rivers began to matter more than raindrops. Instead of a sky that could weep on any day, the world discovered a pattern where wet and dry alternated over months and years. The change came with more organized continents and with them mountain ranges. Elevated topography encourages monsoons, and monsoons are a compromise between deluge and drought. In such a scheme, the atmosphere saves up moisture and then spends it in concentrated bursts as rising warm air funnels into cloud towers. The emergence of a climate of rivers did not cancel the ancient taste for water. It merely concentrated it into seasons, carving floodplains, building deltas, and delivering chemistry in pulses that living things later learned to anticipate. In a sense, the world traded constant background rain for the music of storms and the logic of catchments. As rains poured across basalts and komatiitic rocks in those earlier ages, water began as a weak acid. Carbon dioxide dissolved into the drops created carbonic acid, while sulfur dioxide and nitrogen oxides from eruptions sometimes sharpened the bite. But acids are hungry, and the planet was a banquet of fresh minerals. Rapid weathering fed rivers with cations that neutralized the water, turning an acid wash into a buffered solution. Bicarbonate carried carbon away to the sea, where it found calcium and formed carbonates that stacked into nascent platforms. As the cation budget swelled, oceans grew less corrosive. That softening of the chemistry likely expanded the areas where delicate organic molecules could persist. over time, rain went from a dissolver of worlds to a builder of stable waters. Shorelines have their own biographies, and in a world of ceaseless rain, they began as bruised lines where waves met soft new rocks. Without rooted plants to bind it, the coast yielded easily to attack. Storms piled sediments into pocket beaches that disappeared in the next gale. Tides, once the modest sloshing of a young ocean, amplified in narrow embayments. Sandbars learned to migrate, cuspate spits tested the geometry of the wind, and submerged banks became laboratories for flow. These earliest beaches and tidal flats were shaped by prestige forces alone, the moon and the wind and the pressure fields of weather. Later, as microbial mats colonized the intertidal, the shore acquired memory. Structures that would look like ripples and stromatolitic wrinkles to our eyes became common. The coast transformed from a boundary to a workshop. To the surprise of generations of geophysicists, the deep earth appears to keep its own water chest. In minerals such as ringwoodite, a high-pressure cousin of olivine that forms hundreds of kilometers down, hydrogen atoms can nestle into crystal lattices. Laboratory studies and seismic observations suggest that the mantle transition zone may store an amount of water comparable to the modern oceans, not as liquid, but as structural guests in solid stone. During the long, rainy age, this geologic pantry likely mattered. Subducted slabs carried hydrated minerals downward, while upwelling mantle released water through degassing and through the metamorphic unbinding of those same minerals. The deep and the surface were in conversation, trading moisture across eons. The notion that some of the ocean was borrowed from the interior and some of the interior later borrowed it back makes the story of rain richer and more cyclical than a sky-only tale. Of course, not every researcher accepts a marathon deluge as the only path. There are other coherent stories. One pictures an early ocean delivered in large part by a sustained drizzle of water, rich planetesimals, with volcanism and sporadic condensation balancing losses to space. Another sees short, intense spells of rain separated by long, humid interludes in which the atmosphere held most of its water aloft as steam. There is even a school that grants more agency to chemistry at the surface and within the crust, where reactions such as serpentinization and alteration of basalt could both consume and later release water, smoothing climate swings without relying on an unbroken rain. The competing scenarios are not enemies. They are alternate arrangements of the same orchestra. In each, the instruments are familiar: degassing, delivery from space, loss to the wind of the young star, and the feedbacks of rock and cloud. What none of the scenarios erase is the legacy, millions of years of wet weather left behind an ocean with the ionic makeup that underpins modern physiology. Life later borrowed sodium gradients to power nerve signals and borrowed calcium carbonates to grow skeletal parts. The climate learned from that era how to regulate itself through the silicate weathering thermostat, a feedback loop that still hums quietly in the background of our age. The crust acquired thickness and compositional diversity through cycles of hydration and melting, seeding continents that would become platforms for ecosystems. Even our cultural imagination owes debts to that distant rain. Wherever we tell stories of cleansed worlds, of floods that reset the calendar, we are echoing a geological truth. Water had once been the editor of everything. when the rain finally stepped back from constant to seasonal, when skies cleared long enough to see stars not as pale coins but as pinprick fires, the planet was already mature. Oceans covered much of the surface. Rivers braided silts across lowlands. Hydrothermal chimneys labored at the margins between crustal plates. Islands of stabilized crust lifted like dark rafts in a world of blue. In that cosmography, the first self-copying molecules could find both shelter and stimulus. A warm pool poised between evaporation and refill by the next storm could concentrate organics to the threshold of reaction. A porous basaltic shoreline could provide a labyrinth of micro-spaces where proton gradients and mineral catalysts built the primitive versions of pathways that much later would be named metabolism. The rain did not write life, but it copied a scaffold that life could later use. We sometimes look at a satellite image of the modern world and imagine that this is the normal state of Earth, water and land in balanced patches, cloud arms swirling in storms that fade in a week. Yet the oceans we know are fossils of a long apprenticeship. The calm that movies and maps sell is a present that the past purchased with time, energy, and deluge. This knowledge does not make the present less beautiful, it makes it more. When the first raindrop after a drought hits soil today, it still obeys equations set back then. When a child tastes a grain of sea salt on their lip at a windy beach, they taste a recipe that was perfected when continents were rumors and thunder had nowhere to echo but the open sea. Thank you for spending these moments in the company of an ancient storm. May the steady cadence of that planetary rain follow you into rest like a faraway shower on a night roof, soft and reassuring. Sleep well and let the distant sound of the first oceans become your quiet.